Picture a universe frozen in absolute stillness, a realm without dance, without rhythm, without life. No planets tracing their celestial arcs, no stars bursting into brilliant supernovae, no galaxies swirling in their majestic cosmic ballet. The very thought seems not just improbable, but fundamentally impossible. Movement is the heartbeat of existence, the fundamental language through which the universe communicates its most profound secrets. Long before we understood these secrets, Isaac Newton unveiled a revolutionary understanding of motion that would transform human comprehension forever. In just 3 elegantly simple laws, he decoded the underlying choreography of the physical world, explaining phenomena as diverse as an apple falling from a tree and massive stellar bodies rotating through infinite space. These are not abstract mathematical concepts, but living, breathing principles that manifest in every moment of our daily experience. Consider the mundane miracle of your morning coffee, when the cup tilts and the liquid threatens to spill, when a sudden bus stop sends passengers lurching forward, when a child's playground swing reaches its apex. These are not random events, but precise demonstrations of universal mechanical principles. The same fundamental laws that govern these everyday moments also maintain the Earth's intricate orbit around the Sun, keep satellites suspended in space, and guide the trajectories of distant planetary bodies. Newton's laws are more than scientific abstractions. They are a key to understanding the hidden mechanics of our reality, a blueprint that reveals how objects interact, move, and transform. From the tiniest subatomic particle to the most massive galactic structure, these principles explain the fundamental dance of matter and energy that underpins our entire existence. Imagine unraveling these mysteries, peering behind the curtain of physical reality to understand the elegant mathematical poetry that governs all movement. Whether you're puzzling over why it feels so difficult to rise from a comfortable sofa on a lazy Sunday morning, or wondering how astronauts seemingly defy gravity in the vast emptiness of space, Newton's laws offer profound insights into the mechanical ballet of our universe. This is an invitation to a journey of discovery, to explore how 3 revolutionary laws can explain the movement of everything from falling apples to exploding stars, from the momentum of a child's swing to the orbital paths of distant planets. Are you ready to unlock the secrets of universal motion? Imagine a fundamental property of matter so profound that it challenges our intuitive understanding of movement, the principle of inertia. Newton's first law is like a stubborn character in the cosmic narrative, declaring that objects possess an inherent resistance to changing their state of motion. It's a law that speaks to the fundamental laziness of the physical world. An object at rest wants to remain at rest, while an object in motion yearns to continue its journey indefinitely. The brilliance of this law lies in its counterintuitive nature. In our everyday experience, we observe objects naturally slowing down and stopping. A rolling ball eventually comes to a halt, a moving car gradually decelerates. But Newton revealed a deeper truth. These observations are misleading. In the absence of external forces, an object would continue its motion or rest eternally. Let's dive into a vivid illustration. Imagine you're riding a bus that suddenly applies its brakes. Your body lurches forward, not because of some mysterious force, but because of pure inertia. While the bus comes to an abrupt stop, your body wants to maintain its previous state of motion. This is inertia in action, a testament to an object's inherent tendency to resist changes in its motion. Real-world examples of inertia are everywhere. Tablecloth trick. When a skilled performer quickly pulls a tablecloth from beneath dishes, the dishes remain in place, demonstrating how objects resist sudden changes in motion. Seatbelts. These crucial safety devices exist precisely because of inertia. In a sudden stop, your body wants to continue moving forward. Space travel. Astronauts experience minimal resistance in space because there are virtually no external forces to interrupt their motion. The profound implications extend beyond simple mechanical observations. Inertia is a fundamental property that connects the microscopic world of subatomic particles to the vast movements of celestial bodies. It explains why planets continue their orbital paths, why a spinning top maintains its rotation, and why objects in deep space can travel vast distances with minimal energy expenditure. Inertia is not just a scientific concept. It's a metaphor for resistance to change, a principle that resonates beyond the physical realm. In your daily life, where do you observe objects, or perhaps even yourself, resisting changes in motion or state? Every time you push a heavy object, every moment you feel the resistance when trying to start or stop movement, you are experiencing Newton's first law in its most tangible form. It's a universal principle that transforms our understanding of motion from a simple observation to a profound philosophical and scientific insight. The law invites us to look beyond the apparent and recognize the fundamental interconnectedness of motion and resistance, challenging our perception of the physical world and revealing the elegant mathematical symphony that governs universal mechanics. Newton's second law of motion represents one of the most fundamental principles in physics, elegantly captured by the simple equation F and ma, force equals mass times acceleration. This profound mathematical relationship reveals how forces interact with objects in motion, fundamentally transforming our understanding of physical dynamics. Imagine the incredible complexity hidden within these three symbols. When you apply a force to an object, its acceleration isn't arbitrary, but precisely determined by its mass. This means the more massive an object is, the more force required to change its motion. Think about pushing a shopping cart. An empty cart responds dramatically to the smallest push, while a fully loaded cart demands significantly more effort to start moving or stop. Rocket science provides an extraordinary illustration of this principle. Space engineers must calculate enormous amounts of thrust to overcome a spacecraft's massive weight. A rocket carrying tons of equipment needs exponentially more fuel and power to achieve the same acceleration as a much lighter vehicle. Every gram matters in these calculations, making Newton's equation a critical tool for space exploration. The law beautifully demonstrates that force is not just about strength, but about the intricate relationship between an object's mass and how quickly it can change its velocity. A gentle push on a feather produces immediate movement, while the same force applied to a boulder might produce almost no perceptible motion. This reveals the democratic nature of physics. The same principles govern both microscopic and massive systems. In practical terms, Newton's second law explains countless everyday phenomena. When a car accelerates, when an athlete jumps, when a ball is thrown, in each case the force applied, the object's mass and its resulting acceleration are dancing together in a precise mathematical choreography. It's a universal language that describes motion across the entire cosmos, from subatomic particles to massive planetary bodies. By understanding this law, we gain insight into how energy transforms motion, how forces interact, and how the universe fundamentally operates. Newton didn't just describe movement, he unveiled the mathematical poetry underlying all physical interactions. The universe operates on a fundamental principle of balance, elegantly expressed in Newton's third law. For every action, there is an equal and opposite reaction. This law reveals the intricate harmony underlying all interactions in the cosmos, from the smallest atomic collisions to the grandest celestial movements. Consider what happens when you walk across a room. With each step, you push against the floor with your feet, and the floor pushes back with exactly the same force in the opposite direction. This reciprocal interaction propels you forward. This same principle explains how birds achieve flight. As their wings push down against the air pushes up with an equal force, lifting them skyward. The more forcefully they flap their wings, the stronger the upward reaction force becomes. In space, this law becomes even more apparent. When an astronaut pushes off from a space station wall, both the astronaut and the station experience equal forces in opposite directions. Since the space station has much greater mass, it moves only slightly, while the astronaut glides away at a higher velocity. This perfectly demonstrates how the magnitude of motion depends on mass, even though the forces remain equal and opposite. Rocket propulsion provides perhaps the most dramatic illustration of the third law. As the rocket engines expel high-speed gases backward, these gases push against the rocket with an equal force forward. This reaction force is what enables spacecraft to accelerate through the vacuum of space, where there's nothing to push against except their own expelled propellant. Even in everyday situations, this law manifests continuously. When you're swimming, you push water backward, and the water pushes you forward. When you fire a gun, the forward momentum of the bullet is matched by the recoil you feel in your shoulder. When you inflate a balloon and release it, the air rushing out in one direction sends the balloon zooming in the opposite direction. Understanding this law has profound implications for technology and engineering. It's crucial in designing everything from jet engines to roller coasters. The same principle that lets a squid jet through water by expelling a stream of fluid enables modern spacecraft to navigate the solar system. Every action in our universe, no matter how small or large, exists as part of an intricate ballet of equal and opposite forces, maintaining the cosmic equilibrium that governs our physical reality. In essence, Newton's third law reminds us that nothing in the universe acts in isolation. Every push has its pull, every action its reaction, creating an endless dance of balanced forces that orchestrates the movement of everything from subatomic particles to entire galaxies. This fundamental symmetry of nature ensures that momentum is always conserved, maintaining order in what might otherwise be a chaotic universe. The true brilliance of Newton's laws lies not just in their explanatory power, but in their astounding universality. These simple yet profound principles govern everything from the quantum dance of electrons to the majestic waltz of galaxy clusters, creating a unified framework that connects phenomena across 14 orders of magnitude of scale. Consider the delicate interplay of forces in a soap bubble floating through the air. Surface tension pulls the molecules into a perfect sphere, while air pressure, gravity, and atmospheric resistance orchestrate its graceful descent. The same laws that dictate this miniature ballet also govern the formation of stars, where gravitational forces compress hydrogen until nuclear fusion ignites, balanced perfectly against the outward pressure of radiation. In the quantum realm, despite the strange and counterintuitive nature of particle physics, Newton's laws still provide a remarkable approximation of particle behavior in many situations. When we scale up to human-sized objects, these laws perfectly describe the arc of a baseball, the swing of a pendulum, or the orbit of a satellite. Scaling up further, they explain how galaxies maintain their spiral structure, how solar systems form, and how vast clouds of cosmic gas coalesce into new worlds. Even in the most extreme environments in the universe, Newton's laws hold true. Near black holes, where space itself becomes warped and time slows down, the principles of action and reaction, force and motion, still apply. While Einstein's relativity may provide more precise descriptions at these scales, Newton's laws emerge as a beautiful approximation that captures the essence of cosmic motion. This universality reveals a profound truth about our universe, that fundamental principles transcend scale. The same mathematical relationships that cause a leaf to spiral to the ground also guide the formation of spiral galaxies. The forces that keep electrons bound to atomic nuclei mirror those that keep planets in orbit around stars. It's a testament to the elegant simplicity of nature's rulebook. In this grand cosmic dance, we witness the ultimate democracy of physics. No object, regardless of its size or composition, is exempt from these laws. A dust mote and a supernova may seem worlds apart, but they speak the same language of force and motion, mass and acceleration, action and reaction. This universal applicability of Newton's laws stands as one of science's most beautiful revelations, that the entire cosmos, in all its spectacular diversity, moves to the rhythm of the same fundamental rules. Newton's laws represent far more than mere mathematical descriptions of motion. They handed humanity the keys to unlock the universe. His work transformed us from passive observers of cosmic phenomena into active participants in space exploration, technological innovation, and scientific advancement. Every space mission ever launched stands as a testament to Newton's profound understanding of motion and forces. When NASA engineers calculate the precise trajectory needed to send a probe to Mars, they're wielding Newton's mathematical tools. The delicate orbital dance of the International Space Station, maintaining its perfect balance between gravitational pull and forward momentum, is a direct application of these principles. Even the timing of rocket stages, the positioning of satellites, and the carefully choreographed gravity assists that allow our spacecraft to reach the outer solar system, all are born from Newton's insights. But the impact extends far beyond space exploration. Modern transportation systems, from high-speed trains to commercial aircraft, rely on our ability to understand and manipulate forces as Newton described them. The design of every bridge, the operation of every elevator, and the function of every automobile engine demonstrates these laws in action. Even the smartphones in our pockets contain accelerometers and gyroscopes that work based on Newton's principles. In medicine, these laws help us understand human movement, leading to better prosthetic designs and more effective physical therapy techniques. In sports, coaches and athletes use Newtonian mechanics to optimize performance, from the perfect golf swing to the most efficient swimming stroke. The entertainment industry employs these principles to create realistic, computer-generated imagery and special effects that make modern movies so compelling. Perhaps most remarkably, Newton's laws have become fundamental to how we understand and predict natural phenomena. Weather forecasting relies on our ability to model atmospheric forces. Seismologists use these principles to study earthquake propagation. Ocean scientists apply them to understand currents and wave patterns. Even in the field of robotics, engineers program machines to navigate their environment using these same unchanging rules. This practical application of Newton's laws represents one of humanity's greatest achievements: the ability to not just understand, but to harness the fundamental rules of the universe. We've moved from simply observing falling apples to launching spacecraft that can land on comets. We've progressed from watching birds fly to creating aircraft that can break the sound barrier. Each of these achievements begins with the foundation Newton provided. In essence, Newton didn't just explain the universe to us. He gave us the instruction manual for it. His laws serve as the foundation upon which generations of scientists, engineers, and innovators have built our modern technological civilization. Every time we send a text message via satellite, board an airplane, or watch a space launch, we're experiencing the practical power of Newton's insight into the fundamental nature of motion and force. His laws have become the toolbox with which humanity continues to build its future, reaching ever further into the cosmos while creating ever more sophisticated technologies here on Earth. Every movement we witness, from the gentle sway of leaves in the wind to the rhythmic beating of our hearts, tells the same story: the story of Newton's laws orchestrating the cosmic ballet that surrounds us. When you observe a child on a swing, You're watching the same gravitational interplay that keeps the moon in Earth's orbit. When you see steam rising from your morning coffee, you're witnessing the same principles of motion that drive massive solar flares on our sun's surface. This universal choreography connects us all in ways both profound and poetic. The blood flowing through your veins follows the same fluid dynamics that shape Jupiter's great red spot. The forces you feel while riding a roller coaster mirror those experienced by stars as they orbit the supermassive black hole at our galaxy's center. We are not merely observers of these cosmic laws, we are living expressions of them. Understanding this connection transforms our perspective of the universe. No longer are we separate from the cosmic drama unfolding around us. We are integral players in it. Each breath we take, each step we make, each gesture we perform adds to the grand symphony of motion that echoes across the cosmos. These laws don't just govern our actions. They are the very language through which we interact with reality. The exploration of these universal principles never truly ends. Each new discovery in physics, each advancement in space exploration, each breakthrough in technology adds another layer to our understanding of these fundamental laws. As we continue to push the boundaries of human knowledge, we find that Newton's laws serve as our faithful guides to even greater mysteries. Next week on Exploring the Universe, we'll embark on an exciting journey into the frontier of exoplanet discovery. We'll uncover how scientists use Newton's laws to detect planets orbiting distant stars. You'll learn how the subtle gravitational dance between stars and their planets creates observable patterns that allow us to identify new worlds thousands of light years away. We'll explore how the same principles that explain a pendulum's swing help us understand the complex orbital mechanics of multiple planet systems. By subscribing to our channel, you'll join a community of curious minds exploring these cosmic connections. You'll discover how the physics we observe in our daily lives scales up to explain the grandest phenomena in the universe. From the physics of black holes to the mechanics of planetary formation, from the birth of stars to the death of galaxies, each episode brings you closer to understanding your place in this vast cosmic dance. Don't miss out on this continuing journey of discovery. Subscribe now to Exploring the Universe and join us as we unravel the mysteries of our cosmos, one law of physics at a time. Together we'll explore how these eternal principles, first recognized by Newton, continue to reveal new wonders about our universe and our place within it. Every movement you observe, every force you feel, connects you to the greatest show in existence, the endless dance of the cosmos. And the best part, you're not just watching this show, you're part of it. See you next week as we continue our exploration of the greatest mystery of all, the universe itself.